Buenos días a todos. Bienvenidos a un nuevo seminario del Symposium. Today I changed to English. Today I'm pleased to announce today's talk. It's going to be given by Professor Molcard. She's working at the Mediterranean Institute of Oceanography at Toulon University, and she's going to talk about what to do with 10 years of gappy radar data. So, Anne, whenever you want, welcome.
Thank you. Do I have to keep the mask?
No, I think you can remove it.
Is it okay?
Yeah.
Okay, well, thank you very much, Hanno. Thank you for inviting me, and thank you also to University of Balearic Island for inviting me in this framework of invited professor. So now I could taste spring in Mallorca, actually, which is quite strange because the weather is really cold, but I hope that it will get better. So today I would like to present you some results about HF radar analysis. So the radar, I will focus on the system that is installed in Toulon since 2010, so more than 10 years now. And I will give you some illustration of what we have been doing in the last years. A lot of people have collaborated in one way or the other to this presentation since 2010. But today I will focus on the results of Natasha Bourg, which is doing a PhD with me, and Alejandro Cáceres-Euse, who is doing a postdoc in Toulon. So, I don't know. Okay, so first, just let's look at the region of interest, which is the Northwestern Mediterranean. So, well, you all know, since it's also your playground, most of you. So the Northwestern Mediterranean is characterized by a very rich circulation. Mediterranean is called a laboratory in terms of physical oceanography because in a reduced sea, you have all the physical process. And it's easier to measure and to observe Mediterranean than big oceans. So the main circulation is characterized by the northern current, which is a current along the coast, which is part of the cyclonic circulation of the Western Mediterranean Sea. It flows along the continental slope and in geostrophic balance at first order. It's also a baroclinic current, ringing and flowing, having the three major water masses of the Western Mediterranean, which are the Atlantic water, surface waters, the Levantine intermediate waters, and the Western Mediterranean deep water. So this boundary current is very strong. It's called the northern current, but also the Ligurian, Provençal, Catalan current. It has a big role in terms of transport, both barrier or carrier of transport. The region is also characterized by deep water formation, which is it's quite rare in the ocean. The northern current has a very well-known large-scale signal. So it has a very strong seasonal signal. It is stronger, closer to the coast, narrower and deeper in winter than in summer. And associated with this large-scale structure, you also have mesoscale and submesoscale activity. So what do we use as toys to analyze the circulation in our regions? We do have at our university and in our lab different means. So we do have numerical models which are run locally. So we do have 3-level nesting. So we use operational simulation. So simulation coming from operational model as open as boundary conditions. So either Mercator Ocean or Copernicus data. And we force first Gulf of Lions configuration at 1.3 kilometers resolution. And then we have nesting going around, this is Toulon region, Toulon coast at 400-meter resolution. And then a third nesting at Toulon Bay at 100-meter resolution. So these models are hydrostatic configuration. They allow us to play at different scales and work on different dynamics. Additionally to numerical models, we have observations. So mainly in my group, we are working with 2 kinds of observation. Drifters, so surface drifters, either launched directly from Toulon, so very small and regular experiments, or also, thanks to the northern current, we can also have information from drifters that have been launched from Italian partners, for instance. And they are passing through our region, so we can use this data. And of course, we have also this fancy instrument, which is HF radar. So HF radar is a remote sensing land system. So it works as an antenna emitting electromagnetic signal, which is reflected by specific waves, the waves that have half the wavelength of the emitting frequency. So according to Bragg's theory. So the system that is installed in Toulon is a WERA system, which is called the European radar. So the difference between WERA and the American coder system is that WERA needs long antenna arrays. So you need a lot of space. But the counter nicer part is that you can, it's really open source system. So you can work both with currents, but also waves and also wind, and you can adapt the system on your personal interest. So the Toulon area is quite complicated as a coastline because we have islands and there are no really big beaches where you can install it. So we had to find a way to install this long array system. And that's why we use a multistatic system, meaning that you don't have the emitter and the reception at the same place. So actually we have 2 emitters and 2 transmitters. And this multistatic allows you to have multiple possible radial maps. So the one antenna or one system gives you the radial component, meaning the projection of the total surface current, the projection on the looking direction of the radar. So it's only one component of the surface current, so you need at least 2 radials overlapping to get the surface currents. So here you have the example of 2 radial maps, which gives you the radial component, so one variable. And here is the resulting surface current. So the radar gives you spatial and temporal resolution. It depends on the frequency you are using. In our case, we have a bandwidth of 100 kilohertz, giving a resolution of about 1 degree, the azimuthal resolution, and 1.5 kilometer resolution. So in total, when you reconstruct the surface current, you can have maps of 1 kilometer of resolution. Okay, so the radar, like any other instruments, can have some failures. There are a lot of antennas, meaning that they are very sensitive to the weather. And so you need, of course, electricity, electrical power. And so since 2010, we had a lot of failures. Moreover, you can have one antenna that is working and the other one is not working. So you have only half information. But it's true for every data, of course. So the first thing is that you need to do some level processing. So I have listed here the different data that you can have. So you have what we call L0. So it's the raw hourly high resolution data. And then you start to increment and analyze and do some statistics and some filtering to get more complete in time and space data. So you remove outliers, you try to apply filling methods, then you can do daily mean to have less noisy data, and then you can go to more complex filling methodologies like DNOF, and also you can either use the radial velocity or the vector data. So since the beginning of the installation, there have been a lot of works on this data. So here I have listed some examples. So we try to assimilate the HF radar, not to correct the direct surface velocity field, but try to correct either the open boundary condition or the wind forcing. We did with Hanno or Fila forecasting of HF radar data using genetic algorithms. We did a lot of validation with drifters in the framework of European project, trying to set an observational system. And we can also do a lot of comparison with models, but also with other kind of observation. So here I will focus on 3 recent examples. So the analysis of the whole 10 years time series HF radar data. Some example of the trendy artificial intelligence method to decompose the surface velocity in a physical way. And also, I will say some words on multi-platform and connectivity. So 10 years of data. So here again, you see 2 examples of hourly radial data. And here is the temporal coverage. So the red dots are one radial and the blue dots are the other radials. So you need 2 radials together to get the vector. So you see that sometimes you have only the red and not the blue. And sometimes you miss both. Hopefully, sometimes you also have the 2 working together. But there are a lot of gaps. So the first thing we did is to apply DNOF, which is a filling method based on empirical orthogonal functions. And since the time series is very long, you can have different time scales included in this reconstruction. So we filled the data completely to have at least daily data filled spatially and temporally. Then we look at the time scales of variability. We look also at specific events. And focusing on eddy demography. So once you have this big time series, you can do power spectrum density analysis to look at the time scale variability that is included in your data set. So if you look at hourly data, so it's not completely filled because hourly data, I mean, can be scattered, but you can work on and make and look at frequency, very high frequency, like inertia, tides or land sea breeze. And here you can see 12, 17, 24 hours, which are very much correlated with the wind frequencies. And if you focus on the daily complete data set, then you can focus on more large scale, like larger time scales, like seasonal and interannual large scale. So here you see 6 month or year time scales. Of course, you can also look at climatology. So for instance, here you have an example of daily climatology. So this is the velocity magnitude along this section crossing the boundary current and along the year. So what you see is simply what is written in bibliography, meaning that saying that the northern current is stronger in winter than in summer, and it is narrower in winter than in summer. So you can have information both at annual time scale or more higher time scales. So now I'm showing you some very specific events. So those are daily maps. So on the left side, you see daily maps at different days. On the center, you see the same date, but filled with DNOF. So this is to check if this methodology works well or not. And on the right side, you have the model. So the resolution is similar between the model and the radar. And of course, I have picked up some dates where it works very well, but this was also my goal. So here you see the daily map, which can have different spatial coverage according to the date because of the weather, because of the electromagnetic signal. Here you have DNOF reconstruction, so you can see that for very different circulation, so this one is typical of a Mistral wind event, and this is typical of a classic no wind circulation. DNOF seems to work very well, which is normal because actually we do have a map, so actually it should not build something different than the reality. And also the model is doing quite well. So let's see two other situations where you only have one radial. So here you have one radial and here you have the other one, meaning that we are missing one component of the total velocity. This is what DNOF is reconstructing using only this radial and also all the other time series. And this is the model. And actually, it seems, if we trust the model, that DNOF is doing a good job. And it's true for both situations. Of course, if you have long periods where the radar is not working, well, DNOF cannot do miracles. So you should also be careful about this reconstruction, but still is doing good work. Okay. Since we have noticed that there are a lot of small-scale structure associated with this boundary current, we apply a eddy detection algorithm. So from Nencioli et al. Method, but there are plenty of methods nowadays. So you see that this is the northern current. So this is HF radar map, and very often we have this anticyclonic eddy appearing and disappearing. And we also sometimes have cyclonic eddies south of the northern current. So the detection algorithm will help to look at every map and identify if there is an eddy according to geometric conditions. And you can work on the seasonality of this eddy appearance. What we wanted to focus on is to look at the eddy occurrence, variability, and how they depend on the northern current. So here you have a map of the velocity from the HF radar, and here you have a line which represent the maximum of the northern current in terms of velocity magnitude. And the color will represent the position. So the position in latitude. So if it's red, it means that it's a little bit south. If it's blue, it's a little bit north. And here you have along the time, you have the position of the northern current along longitude with the same color, the same color. So if it's red, it means that it's south. If it's blue, it's north. Overlapped to this map, you also have these triangles, which are all the events of eddy occurrence during this period. So if it's red, it means that the eddy is south. If it's blue, it means that the eddy is north. And also you have the triangle. If it's upward, it means that it's cyclonic. If it's downward, it means that it's anticyclonic. So this figure, which is a little bit complex, there are a lot of stuff inside, but the idea is to see if the appearance, the occurrence, and the type of eddy depends on the northern current undulation and curvature. And what you see is that actually the anticyclone are always north of the northern current, since they are blue on a red background. And the cyclone are always south of the northern current, because you have the red triangles over the blue background. And it's quite logical, because you see the undulation of the northern current. And so if the currents go westward, of course, you may have here a cyclone, and here you will have an anticyclone. So from this Hofmüller diagram, you can also look at the displacement of the northern current and the displacement of these eddies. And you can see that, for instance, the cyclones are displaced faster than the cyclone because the slope is bigger. Okay, so you can work on this eddy appearance and propagation. Okay, so this was a zoom over the two specific events. Okay, next step will be to work on the third dimension, because radar is giving very nice surface currents, but only at surface. So can we have information on the third dimension, on the vertical dimension? Of course, you need something else. You need either measurements on the vertical, or you can have help from the model, keeping in mind that models, of course, can have some errors. So next step will be to work with the models. So here you have a map at different depths of salinity from the model, and you can see the signal of the eddy. And my question today is, how deep are these eddies? So we can detect them at the surface. Do they have a vertical structure? And then, of course, it is correlated also to vertical velocity. So you can work with the model, and you can also work with other surface information like satellites. So here you have chlorophyll information overlapped with the HF radar map. And all these together will help us to understand the mechanism of this eddy generation. Okay, second part is about artificial intelligence for velocity decomposition. So what Dr. Alejandro Cáceres did, it was to apply the self-organizing map artificial intelligence, well, it's a machine learning technique, to the HF radar data. Combine sometimes with the wind, sometimes with the waves, and we had different goals in using this. Our first goal was to try to decompose the total velocity observed by the radar in the geostrophic and ageostrophic part. So the goal of this work was to combine the radar and the wind. So we did the joint sum analysis, mixing radar and wind. So wind, which comes from meteorological models. And the goal is to identify features which are characterized by strong wind or no wind. And the hypothesis is that when you have surface current with no winds, this may be the geostrophic component. Okay, this is our hypothesis, and we will try to prove it. So the hypothesis is that circulation with no wind is geostrophy, so meaning that circulation with wind, strong or mid, it's dominated by ageostrophy velocity. So here you have the extraction. So the sum is a methodology that helps you to reduce the dimension of your data and extract the main features. So here you have 4 neurons among many others. Actually, it was 9 neurons decomposition. And here you have 4 different situations. So you have a typical, so the wind is in red and the radar is in black. So here is a easterly wind. So you have a very strong westward northern current. And here you have a typical Mistral wind, which is northwesterly wind. And then the circulation, I mean, you don't see anymore a very clear northern current signal because of the wind. And this 4th situation, you don't see, well, the wind is very low. And then you can see the classic northern current signature. So our hypothesis is that the neuron that presents a circulation with low wind and higher occurrence is the one that we will consider the geostrophic component. Okay, so we extract this neuron as the geostrophic component. And then we will try to prove it because, of course, I mean, the decomposition has some errors because no wind does not mean only geostrophy, and a lot of wind does not mean only ageostrophy. The 2 components are always together. But the idea is to extract as many geostrophy as possible or as many ageostrophy as possible. So here we compare the velocity from the radar according to the neuron. So here is neurons with no wind, and on the right panels is neurons with wind. And we compare it with the ageostrophic component computed from Ekman theory, so from wind, and from Stokes theory, so from wave data, wave model actually. So the red one is the radar velocity. from the neuron with no wind. So what we suppose the geostrophic component. And in black points are the ageostrophic velocity computed from wind and Stokes drift. And what you can see is that the geostrophy is much higher. And the ageostrophic component is very low. On the other side, when we look at the wind pattern, so neurons with strong or medium winds, the red one is the radar, and the black one is the ageostrophic component computed from wind and waves. And you can see that they are the same order of magnitude. So our conclusion is that actually what we extract seems really dominated by geostrophy. So another way to validate our methodology is to compare with satellite data. Because actually this was one of the goals, is to use this HF radar to validate, calibrate satellite data. So here we use altimetry data, so geostrophic velocity computed from sea level anomaly from altimetry mission. So those are gridded data from Copernicus database. So it merge all missions, past mission, and you can have gridded maps of geostrophic velocity. And we took 3 points. We pick 3 points and we do the comparison. So the red one is what we extract from the radar and consider our geostrophic velocity, and the black one is satellite. So of course, when you go close to the coast or very far, you can have some errors. But if you focus on in the middle point, P2, or the southernmost point, what you see is that actually you can see the seasonality of this geostrophic current, which is comparable to the satellite information. And you can also so this is the time validation. And if you do the spatial validation, so here you have the radar map in red and the satellite geostrophic velocity in black, you can also see some similarity. Of course, they are not exactly the same because they don't have the same resolution, but in terms of magnitude, they are similar. So this opens nice avenues for new research in terms of satellite validation based on HF radar, which are very coastal data and very high resolution data, so can be complementary to altimetry data. Okay, last point is multi-platform observation. So this is another very trendy thing that we are doing in physical oceanography, is try to mix all the tools that we have. So modeling, observation, and now artificial intelligence. So here I'm showing you another example of use of HF radar. So this was to validate somehow the nesting methodology of the model. So here you have the large scale, the regional model, which is 1.3 kilometer, and then you go higher and higher in the resolution. So here is 400 meter, and then you have 100 meter. And so this is in terms of kinetic energy or eddy kinetic energy. But what you can, and also I've added here in the right panels, the radar. So the radar, I consider it as ground truth. And then I'm trying to evaluate if the model is giving similar, order of magnitude at least. So what you can see is that the radar here gives you very stronger energy. And this is well known that the models are not giving, under-evaluate the energy. But if you, I'm sorry about the colors, but if you go if you look at the zoom, so this is the eddy kinetic energy for the winter mean, what you can see is that at 1.3 kilometers, we have very low energy. at 400 meters, it increased, it's almost the double. And then if you compare with the radar, and if you go at Toulon Bay, 100-meter resolution, the order of magnitudes are getting closer, which is also normal because actually you are increasing the resolution, so you are taking into account more dynamics. But still, actually, we are showing it. And what would be nice is to merge all this stuff. So the radar, all the observation available with the model. So connectivity is another kind of application of all our tools. So connectivity can be in terms of biological connectivity or pollutant impact. So here is an example of Lagrangian virtual particle simulation. Just try to understand how much the boundary current from the large-scale Northwestern Mediterranean Sea can bring into the Toulon Bay. So for instance, if there is an oil spill in Italy, how much will enter the Toulon Bay? Or in the other way as well, Toulon Bay is a quite polluted bay, and very close to the Toulon Bay, there is a national park, protected national park. So we can also ask ourselves, okay, how much of the chemical pollutants from the Toulon Bay can reach the natural park? And of course, to do all these Lagrangian measure, well, you need surface currents. So you can use it from the model, but you can also use it from the HF radar. So you can also work with the connectivity using self-organizing map machine learning algorithm. And this is an ongoing work. So what we are trying to do is to mix all the data that we have. So we have the radar, we have the wind, we have the wave models, and we also have some ADCP data, which are in the Toulon Bay. And so the idea is to combine all the available information and to find connection between the inner bay and the outer circulation based on the radar information. So you have different methodology to use some, but what we have chosen is to you use some based on the ADCP and the wind, so the inner bay circulation. So you have data, wind data and ADCP data. And then some gives you patterns, but gives you also the time series of these extra patterns. And from this time series, you can reconstruct and estimate the mean wind forcing responsible for these patterns. And you can also go back to the surface currents from the HF radar based on this time series and try to get some schematic surface current circulation according to the wind. So you have the circulation inside according to the wind and according also to the outer circulation based on the HF radar. So you get some schematic circulation. So according to the very typical wind we have in the region, either westerly or easterly. And sometimes it can go inside the bay, sometimes it doesn't go inside the bay. And this sometimes, of course, is given in terms of percentage of some of patterns occurrence. Okay, so my conclusion is that, well, the radar, I mean, I think it's an outstanding observational system, but it's very costly. It's difficult to sustain, and also actually it needs some treatment because it's data, and because actually we have very often some failures. But of course, it's very useful for environmental, societal application because it's surface current observation at synoptic scale and it's very rare. But it's also very useful for science. And I think nowadays we have a lot of data from HF radar, and actually it's really time to work in terms of science with this data. Okay, now we have a quite big Northwestern Mediterranean network of HF radar. So, well, we are very happy about this. What is next? So next, I think all of us, we are trying to combine all the data we have together. So, and using artificial intelligence, probably it's also a good idea. And I just finished with a project that I have to submit by today. And I hope, and so I have some colleagues here in the room that will be partners of this project. So this project will be submitted to the French satellite special agency, so CNES. And the idea is to combine, again, different information from physical oceanography observation, so model, observation from HF radar, and satellite information. So both altimetry information, but also SAR images information, which gives you radial velocity as well. And we will combine all this together using either self-organizing map or supervised machine learning techniques, so a little bit more complex, trying to reconstruct total velocity field over the whole Northwestern Mediterranean, based on different HF radar systems that are installed along our coast. And I hope it will be successful and we will work together. Okay, thank you very much.
Thank you very much, Anne. Is there any question in the room? And if there is, please speak loud.
One is about when you decompose the geostrophic component, the currents, why you don't use the divergence, the condition of the divergence of the total velocity, and then to start which situation where it's zero to start the geostrophic velocity?
No, I don't add any condition before, but actually there are other techniques also to compute geostrophy from total current. One of the oldest technique is just to average. So because I mean, geostrophy is the large scale and circulation, but there is also, for instance, OMA method, which separate in non-divergent and non-rotational. And actually, you can also use you can also base your decomposition on this hypothesis. But from our point of view, no, we didn't separate any. We didn't do any analysis before. We put the raw total velocity, and we combine it with the wind. So we put the HF radar current with the wind together, and actually we try to, of course, work on the parameters of some, which actually we have a lot of parameters, trying to get the one neuron with the higher occurrence and with the lowest wind. Yeah, Ananda had a question before, but well, I don't know.
Okay, thanks a lot. And I also agree that HFR is an outstanding platform. And I'm particularly interested, well, I had several questions, but the first one is about the spectra that you have shown. So the temporal scale that we saw, because we have such a nice data set of 10 years, so we really can look at different time scales. But I'm really interested in the high frequency, so from hours to days. And so in this, I don't know if you can go back to that slide.
So yeah, I think here.
Yeah. So you have two different spectra. Can you explain again in this plot?
This one?
Yeah.
So here you have the wind. So this is the spectrum from the wind, and this is from the data, hourly data. And actually, well, we were looking also at the slopes, of course, of the spectrum, because the slopes give you information on the energy cascade. And so actually these slopes are well-known values. So meaning cascade from large scale to lower scale. And well, you can see some specific peaks. So here you have the 12 hours and 24 hours peaks, which are very well correlated with the wind. And this is the land sea breeze hour. And on the data,
Inertial oscillation.
and in yeah, inertial oscillation, you have it here. So we cannot go lower than few hours because actually we have hourly data. Yeah.
And have you tried to separate temporal scales and spatial scales, or do some filtering? Because what's the resolution? The resolution is
1 kilometer.
1 kilometer, so you are resolving scales around what?
A few kilometers, 10, like 10.
Try to filter and see, for instance, separate some mesoscale from a mesoscale, because you are resolving some mesoscale somehow. Filtering spatial scales and look at what are the temporal scales associated to different.
Yeah, actually, based on this, you can go back to the spatial and try to see. Yes, we did it. Actually, in the paper, I didn't show it here, but yeah. Actually, you can really see that the larger scale is the northern current, so it's in the boundary current, and then if you go to the higher frequency, then you have more the eddy part in the northern or southern part of the boundary current.
And also you see some seasonality, no? So you see that in terms of also temporal scales are smaller in winter.
Temporal scale are smaller in winter. What do you mean?
Associated, so well, some mesoscale is stronger usually in winter.
Yeah. Well, actually, we didn't.
Because we are working a lot on trying to determine which are the scales that characterize each process, especially due to problems of synopticity when we do oceanographic cruises. So we want to look, and we are seeing that the temporal scales in winter seems to be like kind of smaller. So the decorrelation scales, because one we do an interpolation. So
okay.
But I was wondering from these observations if you can see this.
Yeah. Well, we didn't do this, but it's a good idea.
Okay. Okay, and yeah, I also had the same comment as Ismail about the hands-on decomposition. So that when you do the geostrophy and ageostrophy, this can be done also with help of the divergence. And I think the people from their papers published, people from ASCII have worked on this. And then last so you use SLA or eddy with altimetry, sea level anomalies?
Well, I use the final product, which is geostrophy velocity.
Yeah, it might be absolute.
Yeah. This is what. Well, my idea today is actually to try to use all the available data, because there is a lot of data available and open data now, open source. So the idea is try to put together and try to find nice results. So that's why I will try to use gridded data, but maybe also a long track data, which is higher resolution. And also there are a lot of promise with SWOT new experiments. So I don't know what would be, but I mean, very, very high resolution. So all this will be nice data to compare with the radar data.
I have one question from one of our students who's online, and he's asking, so Eugenio, he's working also on machine learning, and he's asking about how do you choose the number of neural networks?
Well, it's a good question. By trying, this is trying, and of course, if you have less neurons, you have less situation, less variability. It's like principal component decomposition, actually. So if you have a lot of neurons, it may be useful, for instance, for filling method. Actually, there have been papers using also some for filling methods, but then you need to take into account more scales. For us, the important thing was to separate the major wind regimes. And so, I mean, we found a compromise between 9 and 12 neurons.
Mhm.
Yeah, Hanno.
No.
Yes, I have another question on the DNF method.
Yeah.
How many data you need to
How many?
use this? How many data I mean, to fill the gap? This method needs data
Yeah.
to put there. How long has to be the time series of
So the filling method for the 10 years data, we did a daily mean before. So you had daily mean for 10 years. So then we could keep into account the interannual variability and the seasonal variability down to the daily variability. And so we could reconstruct, so to get this kind of variability, so at higher frequency, we didn't apply DNF because then, I mean, you can do it, but then it's hourly map and then the gaps are too big to fill in. So we can use it, but on shorter periods. But for the 10 years data set, the idea was to use as much as data as possible, but on a daily mean. So it's a long time series, it's 3,650 data.
Another question is in the work about the connectivity, if you need the data, the time series is filled out, the complete trajectories of virtual particles, you need a time series filled.
Yeah.
So you fill with DNF, and then my question is, you analyze the impact of this gap filling methodology temporal, not spatial, the temporal, the temporal dimension on the Lagrangian assessment of the sound dynamics, the connectivity.
Yeah. Well, what I have shown you, the box, have been done with the model. Okay, so those are the models. So we have the 3 nesting models, and so we have hourly output, and we applied CMS Lagrangian module, so offline, but so you have an hourly time resolution of the model, and actually the time to go from this eastern part to the inner part is very short. It's a few days. Maybe I didn't understand your question, but
my question is,
so the model is filled, is completely filled.
But you use also HFR data.
Yeah, the HF radar was used more here. So here you don't have really Lagrangian stuff. Here you just have schematic circulation. Okay.
Yeah.
In the previous one, yeah, actually here, for to compute this box, we didn't use the HF radar. We only use the model. Of course, you can also assimilate the radar on the model, but actually what I'm trying to use is the most simple methods to try to get some physical answer. Don't know if I succeed, but this is my goal today. Hannah?
Well, before me, there is a question on YouTube about the seal paddle. And he asked, or she asked, or she said, sorry, I would like to ask you if it's possible to repeat the conclusions of the analysis of the velocity decomposition into geostrophic and ageostrophic components.
So this one.
Yes.
So actually, we are applying the self-organizing map together on the HF radar velocity and the wind. Okay, so we tune the parameters and the number of neurons in order to get wind patterns, wind forced patterns, and no wind forced pattern. So here you have an example of easterly wind, westerly wind, medium westerly wind, and no wind. And actually, no wind is our hypothesis. No wind and higher occurrence is our hypothesis of geostrophic velocity. So this is the first step. You are applying some methodology, and then you compare this hypothesis. So neurons forced by wind and neurons forced by no wind with the ageostrophic component computed from Ekman theory and Stokes drift. So you need the wind and the wave data, and you can compute the velocity induced by wind and the velocity induced by wave. And then you compare those, and you can see that the geostrophic velocity computed with our methodology is much higher than the ageostrophic component. So this is the proof of our hypothesis. So I hope now the conclusion is more clear. So the idea is that from the HF radar surface current, you can compute, and there are other ways, but you can compute most of the geostrophic component. Hannah, do you have a question? Or?
Well, it's something related to that, something that Ismael commented before, and also, if you compute the divergence of the total velocity and you compute the sum of the divergence of the total velocity, then if you got, and probably you will get it, a pattern that is zero, since you have the BM used, the benchmarking units, then you can identify when the geostrophy is the most dominant.
Is dominant, yeah.
So it's something that can be also done.
Yeah.
With this fancy technology.
And did you try to use OMA for this decomposition? Because OMA separates non-divergent and non-rotational fields. So you can also use this hypothesis to, well, of course, applying OMA, you need also some tuning before, so you never know, but it can be also another method.
Did you try to infer vertical velocities from the modeling using the divergence of the total field?
Using the divergence? No, not yet, but this is the next step, actually. I think we have a lot of things to do, actually. We have a lot of tools. The difficult thing is that when you compare all these tools, of course, they are never really the same. So the model has errors, the data has errors, the observations are not measuring the same time scale, space scale, and variables. So you have to analyze either of these tools alone, and then trying to merge somehow with your knowledge and also with some methodologies, and you have to try to mix all together. But I mean, there are a lot of things to look at still. That's good because we have more work to do.
Can you check if there's any other question in Facebook or in YouTube?
The Sil Patos says thank you. Now it's much clearer. There are no questions.
So okay. Any other question here?
I can ask later, but about the SAR images. So
yeah.
I'm curious because we have started to looking at SAR images, but I think we really need expertise to get something out of the SAR images, and so I just was curious if you can say a few words on how.
Yeah, actually, there have been a student of which name is Baptiste Domps, who worked more on the radar hardware and electromagnetic waves, and actually he did some comparison between the radial velocity from SAR images, which actually is a product of Sentinel-1. So it's the radial velocity along the track of the SAR, and with the radar. And the comparison, I mean, it's not as good as our comparison with drifters, but it's promising. So the idea is to, and actually the resolution is very high of SAR images. So the idea is trying to, to valorize also this data and to compare it with all the HF radar data that we have it along the Mediterranean coast.
There's nothing published yet, no? Something that you were.
Well, yeah, there are 2 papers showing this comparison. So SAR radial velocity against radar, but it's very new actually. Yeah. So, and very local. I mean, it's one track with 1 day of radar, but actually, I think it would be nice to work on a global data set.
Yeah, great. Thanks.
Okay, no more questions? So thank you, Anne, again.
Thank you very much.
So I hope you enjoy and see you in the next symposium.
Thank you.